Hello everybody, welcome to another video lesson. Today we're going over our linear systems, this time with row operations. Okay, so we're going to look at matrices today. At the end of this video, we'll be able to solve our systems of linear equations using matrices and what's called Gauss-Jordan elimination. Okay, so let's hop right in. Our first concept is this idea of an augmented matrix. Okay, so if I'm given a system of equations like this, we're going to derive an augmented matrix based off of just the coefficients and constant terms of our system. Okay, so for this system of equations, our augmented matrix would look something like this. Okay, now what this means, okay, how these two things kind of relate to each other. Okay, this here, think of this as like my X column. Okay, I'm going to think of this as, say, my Y column, and I'll think of this as my Z column. Okay, and then here I would have my constants column. Okay, and I've got this little dotted line that separates my constants column with any of my variable columns. Okay, now each one of these we call an element within our matrix. Okay, so each number here is an element of our matrix. Now notice on my system of equations, I'm given in the second row 2y minus x. Okay, so I want to make sure that I'm not getting tripped up, and I want to make sure that my x column, okay, represents all of the x coefficients. Okay, so even though I've got a 2y here, okay, in this row, the coefficient for x is -1, so that's why I have a -1 here. So don't just say, okay, these are all of my first coefficients, that'll be the first coefficients of my row, of my first column. Okay, we need to make sure that all of my x's are first, and then my y's, and then my z's, or whatever the variables are, they need to be consistent within where they fall in the columns, okay? All right, and then if we were to take out our constant terms, then we'd be left with what we call a coefficient matrix. Okay, so that's just getting rid of this constant term. I'm sorry, my constants column right there. Okay, so we have row echelon form that we've seen as far as our equations go, our systems of equations, but we also have this row echelon form for matrices as well. Okay, so row echelon form, all of our first non-zeros, okay, in each row are going to be a 1. Okay, so I've got a 1 here, here, and here. Okay, my first non-zero element in each row should be a 1. Okay, and then if I have any rows that are all zeros, okay, like this bottom row here, they need to be in the very bottom row of our matrix. Okay, so I wouldn't want to have these zeros like up here in row 2. If I have a row of all zeros, it needs to be at the very bottom. Okay. Notice how we have the same triangle that we had when we were looking at our systems of equations, not in matrix form. Okay, the exact same triangle is going on. So after the number 1, okay, in each row, if you look in the column, every element below that 1 should be a 0. Okay, so we've got this triangle of 1s, and then every element below our triangle, all those elements are going to be 0. So that's row echelon form. We also have what's called reduced row echelon form, which is often the goal when we're manipulating our matrices, is to get our matrix into reduced row echelon form. Okay, so what that looks like, it's very similar. However, all other elements in a row are going to be 0 except for my 1s. Okay, so the first non-zero element, okay, in each row should be 1, and then all other elements are going to be 0. Okay, now think about what that means in terms of my system of equations. If this was my x column, my y column, and my z column, and these are my constants, okay, what this means is that z is equal to f, right? And y is equal to e, and x is equal to d, okay? So we are effectively solving our system of equations when we can represent them in a matrix and put them in reduced row echelon form, okay? Now the process of getting them into reduced row echelon form, okay, is called Gauss-Jordan Elimination, and we're really just operating on these rows in a very similar way to how we operated on our equations themselves, okay? So we have what's called row operations, so similar to how we named our equations. Now we're going to name the rows in our matrix, okay? So that's very important as far as our organization goes. And then our three main operations we have, we can interchange any two rows, okay? So in this example, I'm interchanging rows 2 and 3. Okay, so we can see how my matrix kind of changes in rows 2 and 3 in the first matrix switch right now. So now this is what my matrix looks like. Okay, we can also multiply any row by a constant. Okay, so in this example, I'm multiplying row 1 by a constant of 1 over 5. I'm doing that, okay, because that's going to reduce this 5 into a 1, which the first non-zero for any row that I want to be 1. Okay, so that makes sense to do that in this situation. And then we can also add, okay, a multiple of one row to another. So here, if I was trying to get this 3 to be a 0, okay, I would multiply -3 times row 1, okay, and I would add that to row 2. Okay, so we can add a multiple of one row to another in order to kind of get rid of or change any element to be 0, if that's going to help us with our solution. Okay, so let's take a look at 3 examples of this. Okay, if I have a system of equations and we're going to solve using Gauss-Jordan elimination. Okay, so first thing I'm going to do is I'm going to take my system and I'm going to make it an augmented matrix. Okay, then I realize I have a 1 here already, but it's a -1. So first thing I'm going to do is multiply this second row by -1. And then I'm going to switch rows 1 and 2. Okay, switching rows 1 and 2. So kind of a two-step process right here in this first step. Okay, so when I do that, my matrix is going to look like this. Okay, rows 1 and 2 switched. Okay, so now I've got a new row 1 and a new row 2. And row 3 stays the same. Okay, and all of the signs for row 1 changed, okay, because I multiplied by this -1. Okay, so now I want to try to get rid of, not get rid of, but make this 4 here a 0. Okay, so in order to do that, I'm going to multiply 4 by row 1, and I'm going to subtract row 2 from that. Okay, and that's going to be my new row 2. Okay, this is going to be my new row 2. Okay, my new row 2. So I have 4, 8, 16, and 4, and then minus 4, 9, 16, and 2. Okay, so when I do that, I get 0, -1, 0, and 2 for my row. And my first non-negative is a 1, is a -1, but again, I want that to be a positive 1, so I'm going to go ahead and multiply that by -1. And when I do that, my matrix looks something like this. So again, this is my new row 2 that we're plugging in right here. Okay, so now I want to get rid of, let's see, the 2 here in my third row. Okay, or I want to make it 0, not necessarily get rid of it, but make it 0. So in order to do that, I'm going to multiply 2 by row 1 and subtract row 3 from that. And this is going to be my new row 3. Okay, this is going to be my new row 3. My new row 3. Okay, so this is what our process looks like. Again, the first non-zero element that I have is this -1. And I just want that to be positive, so I'm going to multiply it by -1. So I have a positive 1 here, but that is going to change the sign of my 7 to a -7. So now my matrix is going to look like this. Okay, so we can see we're kind of slowly getting to this reduced row echelon form. Okay, so my next step, I'm going to take row 1 and I'm going to subtract 4 times row 3 from that. Okay, and this is going to be my new row 1. This is going to be my new row 1. Okay, so this is my operation here, and then my matrix looks something like this. Okay, so we're getting closer and closer with each operation. Okay, so next step I want to get this 2 to be a 0. Okay, so in order for that to happen, I'm going to take row 1 and subtract 2 times row 2. Okay, take row 1, subtract 2 times row 2, and that's our operation here. So my new row 1, this is my new row 1, is going to be this row right here. Okay, so my matrix in row echelon form looks like this. Okay, again, what does this represent? Okay, I've got each column representing each variable. Okay, so this is telling me that x equals 33, y equals 2, and z equals -7. So we would write our final solution out like this. Okay, let's take a look at another example. Okay, we're going to solve this again using Gauss-Jordan elimination. We're given our system. We're going to change that into an augmented matrix. Okay, first thing I want to do here, I'm going to flip or swap rows 1 and 2. Okay, so now my matrix looks like this. Okay, again, labeling my rows so I know what I'm doing here. Okay, so I'm going to multiply row 1 by 5, and then I'm going to add that to row 2, and that's going to be my new row 2. Okay, and when I do that, I actually create 2 zeros here for my elements. Okay, so my matrix looks like this, and since I created those 2 zeros, I'm going to go ahead and swap rows 2 and 3. Okay, so now my matrix is going to look like this. Okay, so my next operation, I'm going to multiply 2 by row 1, and then I'm going to add row 2. Okay, and that is going to be my new row 2, which we have here. Okay, that's my new row 2. Okay, so my matrix is going to look something like this. Okay, so now I'm going to say, okay, row 1 plus 2 times row 2. Okay, that's going to be my new row 1. My new row 1. Okay. So when I do that, I'm creating a 0 here. I'm kind of getting rid of this -2, and I'm making this a 0. That's what I'm doing. I'm just trying to pick an element and trying to get that to 0 each time. Okay. Okay, so now in order to get rid of my 1 here, okay, I'm going to take row 1 and subtract row 3, and that's going to be my new row 1. So my matrix looks like this. And then I'm going to take row 2 and subtract row 3, and that's going to be my new row 3. Again, now I'm trying to get rid of this one right here. Okay, so I'm taking row 2 and subtracting row 3. Okay, and that works. I get rid of that 1, and that becomes a 0. Okay, now notice something. I started off with a system of 4 variables, right? So anytime that happens, we know we can't solve for each one of our variables, right? So in terms of our matrix, we actually cannot get it into reduced row echelon form because of how many equations we had compared to the amount of variables that we had. Okay. So what does this mean? Okay, keep in mind what all of my columns mean. Okay, they're representing each variable, right? And we would write our solution like this, right? Okay, so I'm going to take this bottom row and I'm going to try to solve for it in terms of y. Okay, what this really says is y minus 9z is equal to -10. So when I solve for y, I get y is equal to 9z minus 10. And same thing for my x. Okay, this says x plus 8z equals 3. So when I solve for x, I get x is equal to -8z plus 3. And same thing with w. When I solve for w, I get 2z minus 5. So I've solved for each of my variables in terms of z, and that's really the best I can do here, right? So in this case, we're actually going to be able to write our solution in terms of our variable z. We can see here that depending on what z equals, we're going to have infinitely many solutions for our system. Okay? So a little bit different there. I don't have numbers here. Okay, I have these expressions in terms of the variable z. Okay, and that's going to give me infinitely many solutions. Okay, last example here. This one again a little bit different. Let's take a look at what we've got. Okay, I've got -1 in my row 2, so I'm going to multiply that by -1, and then I'm going to swap it with row 1. So now my matrix is going to look like this. And then I'm going to multiply row 1 by -3 and add that to row 2. Again, I'm trying to get rid of this 3 here, make this a 0. Okay, so that's what my operation looks like, and this is what my matrix looks like. And now I'm trying to get rid of this -2 here. I want that to go to 0. So I'm going to multiply row 1 by 2 and add row 3. Okay, that's going to be my new row 3. So here's my operation, and here's my matrix. Okay, so now I've got this 4 here. Okay, my first non-zero element in row 2 is a 4, and in row 3 is -3. So in order to make both of these 1, I'm just going to divide row 2 by 4, and I'm going to divide row 3 by -3. Okay, so when I do that, I get a matrix that looks like this. Okay, again, thinking about what this means in terms of my system, my equations, okay, each one of my columns is representing a variable, right? So if I were to write out the equations for rows 2 and 3, that would say x minus 8y is equal to -19/4. And then row 3 is going to be x minus 8y is equal to -13/3. So think about that conceptually. I have the same thing on the left-hand side of both of these equations, but I have something different on the right-hand side of each one of them, right? Okay, so this really doesn't make any sense at all. Okay, so in this case, when I have this kind of false situation, right, this doesn't make sense mathematically, so this is not going to be true, okay, we're said to have no solution for our matrix, for our system, okay? So that's it for this lesson. Good luck, guys, with your practice.